This is Randy Sargent. It's the day before the 1996 Seattle Robothon, and he plans to enter the line following contest. There's just one small problem. He does not have a robot. Luckily, Randy knows a thing or two about electronics and comes up with an incredibly simple design. It uses a single 8-pin IC to both read the light sensors and drive the motors. He finishes this robot the night before the contest and enters the following morning. Would this be it? Would his tiny little super simple robot be able to beat complex robots with hours of coding and microcontrollers? Sadly, the robot couldn't win. It came last place in the contest. But it still won many hearts because of its incredible simple design and innovative use of a chip that was never designed to do what it was doing here. And it became a bit of a cult classic after the fact. It got affectionately nicknamed Herbie. It became adopted into the Beam community. It never came from the same kind of origins as a lot of the Beam robots, but its simplicity and kind of misuse of other parts not intended for their original purposes won over a lot of hearts, and there was many different versions built down the road from that. It was actually my first ever robotics project when I was a teenager. I had a book called Junk Bots, Bug Bots, and Bots on Wheels. It was by Mark Tilden and someone else, I think, and that was kind of an introduction to Beam robotics, and then they had a couple projects in there, one of which was the Herbie Junk Bot. So let's look at how this works and then build our own. This here is the chip Randy ended up using, the LM386 op-amp chip. So this is designed as a small audio amplifier to drive a small speaker. The way it works is you connect this to ground, you connect this to positive, and you control the gain across these two pins. You can either link them together directly for maximum gain or put a capacitor of different values to control that. And then you have two inputs here, and this would come from an audio mic or a headphone jack or something like that. And what it does is it decides which one of these is higher. Say this is negative and this is positive. Well, it'll amplify that difference by the amount from the gain selected here and then put this pin out. If it's different enough one way, it'll put out a positive voltage on this. If it's different enough the other way, it will put out a negative voltage on that. And that's how you use it as an audio amplifier. But how Randy went around is pretty interesting. He didn't use it in that way, but he figured out how to make it drive the motors from this single pin and use these as inputs for light sensors. So here is the original Herbie circuit. So you can see it's got a motor wired to positive and then to pin 5, and another motor wired to pin 5 and negative. And then you've got an input here with two photodiodes. So when this is more positive, because this one has more light, you can see they're kind of back to back here, this will act as a positive source of power. So it'll drive more out of this motor, and this motor will drive less because both of its poles are effectively connected to positive. If it's the other way around, this will act as a voltage sink. This motor will drive faster, get more current than this one, and this motor will drive slower. And by putting these sensors in the right place and orientating the motors the correct way, your robot will steer towards light, or by marking these over a line on the ground with illumination, it can steer over top of a line and the robot will follow that. Pin number 7 is actually a bypass. It's for noise reduction in audio signals. We don't use that here because we're not using an audio signal. It should be noted that I believe that Randy's original robot actually used CDS photocells with voltage dividers on these. That will work well for a line following robot when you have kind of no and high and low values, but a voltage kind of a photodiode setup like this will give us a much wider range of light that the readings will actually work for our chip here, because it doesn't really care what size those voltage signals are, it just cares how different they are. So this will work even when there's not very much light or when there's a lot of light. It'll still give a good enough signal for the chip. So that would give us a robot that can find light, but if it bumps into something, it would have some issues. So we can also add this little circuit here. So this takes one of my least favorite electrical components, the relay, a transistor, a switch, resistor, and a capacitor to act as a kind of reversing circuit. So how this works is these motors are still wired to pin 5, ignore my little mistake there, but here they're wired to the common pin of a dual pin, dual throw relay. So these come here, and one side will be connected to positive and one side to negative. But when this relay is triggered, this side will suddenly be connected to ground and this side to positive, so these motors will run in reverse effectively. And the way we achieve this is we take a transistor here and connect it across the relay coil here. And then to trigger that, we have this switch to positive. So we pull this high, triggers this, which puts our robot into reverse. And then of course, once it reverses, the switch will open up again. But this little capacitor here will keep a bit of charge flowing through the transistor, and it'll keep our relay engaged for a set amount of time. If this is a really big resistor and this is a really big capacitor, it'll do it for a long time. If those are smaller, it won't do it for as long. So you can kind of tune the backup time with that. So that means our little Herbie robot will be able to get itself out of trouble most of the time, and then it'll get back to searching for light once the reverse circuit is reset.
Always breadboard your circuits before you start building anything, as this gives you a chance to troubleshoot any problems and make sure all your components work together the way you think they're going to work together. I decided to build this on a prototyping PCB that I had lying around. Usually I freeform all my beam projects, but this is easy. I had one lying around, and it's very similar to how I built my first ever Herbie as well. I'll solder the 9-volt battery on, but I used some double-sided foam tape there as well, just to give it a bit more of a secure attachment. This PCB has a couple different rows on the bottom, so I'll build the reversing circuit on one side of the board, and then the light-seeking circuit on the other side of the board. I used the leads of the components as kind of traces, so I would bend them over and solder them to whichever one needed to connect to it. And this helps to kind of form a bit more of a solid connection. I find with these little cheap PCBs, sometimes the copper can peel off the bottom, so it's good to have a mechanical linkage as well. For the motors, I'm going to build these little pieces of copper or brass, I'm not sure what they are, and solder them on. The motors were soldered together from another project, so I ended up just cutting them off. And then I'll put these little tabs on here, and then that'll attach directly to the PCB. Somehow I lined these holes up exactly first try. And we'll get back to soldering on the components. So the integrated circuit will fit in there, and then I'll solder those legs on the same way. It's a good idea to kind of like familiarize yourself from the top of the board before you flip it over to connect the traces. I decided to make some like fancy looking little jumpers here, but there's actually not that many jumpers on the entire board because it's so simple, and I was able to do so much of it on the bottom. This little 2-row PCB I found, I don't know what it's from, but I'm going to use it to hold my 2 light sensors. So I'll solder them in, and then I'll cut one of the traces here, I think the top trace it'll end up being, and then I can solder to those 2 end sections as the kind of outputs of my light sensing, and then I'll solder to the middle section with a pair of pin headers like this, and then that'll be soldered onto the ground in my main board. That electrical connection doesn't matter, it'll just be a way to hold the kind of eyes there. But it's a pretty convenient way to do it, and I can kind of angle everything in the right place. A couple notes with the light sensors. You want them kind of as wide apart as you can, because the wider they are, the more easily your robot will be able to avoid shadows and issues with what it sees, right? Because the eye will avoid it, and then that'll also let the tire avoid it, or the wheel, sorry. If it's inside of the wheel, like mine are a little bit inside, but if it's much inside, then the wheel can get caught on things as your robot tries to go around it. And also, if your robot works perfectly but hates light and tries and goes toward the darkness, flip around either your the pins which your photodiodes connect to, so the 2 pins on the integrated circuit, just swap those around, or you can swap your motors left to right, whichever is easier on your specific one. I'm going to use this little piece of, I don't know, acrylic or whatever it is, to mount a little front skid and also the reversing switch. So I just cut that out and drilled some holes on the old drill press. This will bolt on, and on the other side, at least on the finished version, it'll only have 1/2 size spacer, and then I'm actually just going to drill a hole through one of my contact switches. I don't think you're really supposed to do that, but it'll allow me to mount it on just one side and have a little loop of wire that comes around the front, so that if it bumps into anything anywhere on the front of the robot, it'll trigger the reverse switch. These are actually just standard little robot wheels, but I pulled the tires off and just wrapped them in a thin section of inner tube. That reduced the diameter a little bit, So it gives it a little bit less top speed, but it makes the robot a bit easier to handle. If it goes too fast, sometimes it can't steer itself quite as well as it should. And that front skid plate is actually just a piece of carpet skid from moving furniture and stuff like that. And then the robot's ready to go. So you can see this is the finished project here. I had this little tail skid thing here because sometimes it would flip over backwards when it went from forward to reverse. And that's kind of like a wheelie bar. And now let's test it out. So you can see that this has some pretty complex behaviors. Again, amazing for how simple these little parts are. It can do a bunch of patterns, and it always seems to have a slightly different reaction to even the same inputs, because it's so sensitive to tiny little changes in position or light or whatever. And so you can kind of see this is where the whole idea of emergent behavior came from. So you have something that's a very simple design, but it seems to exhibit much more complex behavior than you would think from just the components involved. I believe there's something called the Brattenberg machine or vehicle, which is a very similar concept to these. And again, it's kind of to study some of the same things. So it has these very simple inputs, but then you have very complex outputs coming out of that and very complex patterns that kind of arise from the very simple parts that go into it.
And that's it for this Herbie robot project. Super easy little project and super rewarding, and especially it's a good one if you're just beginning into the kind of beam or even robotics sphere. This, again, holds a bit of a special place in my heart as being one of my first robots I've ever made, so I still like to build some from time to time, and it's a surprisingly capable little robot. Although it might not win any line following contests, it's got a lot of potential in other ways. Thanks for watching. I'll see you next time.